trend, and they captured all the patterns. So they're able to make accurate predictions at this rate. For the performance in both data sets, we discovered there is a huge performance gap between the MNIST and the CIFA-10, which could be as a result of or due to complexity of the CIFA-10 dataset, which includes mostly color, which include only color images of different various objects like aeroplane, dogs, and it has a depth of 3. While the MNIST, the images are mostly grayscale, and it's just a handwritten digit. This is what we inferred as, or what we believe is the reason for the huge difference between the performance in these two data sets. And then because the CIFA data set has more complex images with more complex and multiple colors and background colors. So it's more difficult to classify complex color images than the simple grayscale handwritten digits. This is one of the reasons of why the accuracy rate differs much. And then the MNIST dataset has a high learning capability, and high convergence rate, more than the CIFA datasets on training, as shown in the table before. Then, because of this huge gap between the performance, the two dataset performance, the gap between the MNIST dataset and the CIFA-10 is was almost 95, and then the CIFA has 70.74. So the gap between the two is almost 30% gap. So we try to see whether we can improve on this performance. So we adjusted the learning rate from 0.001 to 0.01 to see whether the CIFA-10 dataset will be able to learn more features, so to make more prediction accurate or more to improve on the accuracy. But unfortunately, after increasing from their learning rate from 0.001 to 0.01, we discovered that there is no significance in the performance, no significant change. Rather, the accuracy only decreased. Then this shows that our hyperparameter tuning did not improve the performance of model. And these are for our introduction project, for the introduction part of our project report. This we explore and analyze these two dataset, MNIST and CIFA-10 datasets. We compare the performance of the two, and then these two datasets serve as a standard for evaluating model performance, accuracy, and capabilities in deep learning image recognition project. So the two datasets were used and have different CNN, convolutional neural network design and architecture. The MNIST has about 70,000 grayscale images of handwritten digits, which are labeled 0 to 9, so about 10 category classes. And the MNIST also is about 28 by 28 pixels with grayscale depth of just 1. And the cipher consists of 60,000 color images. The, the cipher 10 image is 32 by 32 pixels with color depth of 3. The purpose of this project for this is to classify the handwritten digits MNIST dataset into their respective class and accurate classes, and to identify objects in the color image of the cipher-10 dataset. Both the datasets has the same, for this project, both datasets has the same model architecture of 2 convolutional layers, 2 ReLU layers, and 2 pooling layers. 3 fully connected convolutional layers each, although the filter size for the MNIST dataset is 5 by 5, while for the cipher is 3 by 3. Because already this is very big, and then we need to use a lower weighted filter to help in the computation. That's why we didn't use 5 by 5 just like in MNIST, because MNIST is just grayscale. Then here in the first part we designed and built they tested our convolutional neural networks on the cipher dataset, and then uploaded in the and first we uploaded the dataset on a Google Cloud platform using the TensorFlow libraries to carry out our image recognition. The detailed design has been shown before. I have shown it before. So here you can see the MNIST has a 25 weight values, while cipher has a 3 by 9. And for the 2D inputs of the convolutional layer is 32 by 32 by 3, as I've explained it before. Yeah, and then for the one-hot encoding, as I explained before in the beginning. For the second part is our comparative analysis of the 2 datasets, which are based in deep learning, fully connected convolutional layers. In this third part, we try to reduce the gap between the cipher dataset and improve on the performance. But unfortunately, our performance, our accuracy dropped. Instead of 70% we got at the first training, we try to 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 increase the learning rate, but the model performance decreased on this cipher-10 dataset. In conclusion, our project's part 4 shows that at the beginning of the training, it was low and then it improved. The reason for this, uh, accuracy, between the low accuracy between the MNIST and the cipher-10 is because the complexity of the dataset in this cipher-10 is more complex, more than the MNIST dataset. And then because also the MNIST is just handwritten digits or grayscale, which takes less time and less computational resources to learn and classify. The simpler the data set, and then the less chance of overfitting. Due to the huge gap between the CIFA-10 dataset and the MNIST, our hyperparameter tuning did not improve the performance. And this shows that hyperparameter tuning alone cannot improve the performance on complex datasets like this CIFA-10. The conclusion of this project, we introduced the background of these two popular datasets based on CNNs, and then we compared the performance. We discovered the huge gap between the two performance. We discovered that the huge gap is almost 30% because of the complexity in this CIFA-10 dataset. And then due to the huge gap between these two datasets in CIFA-10 due to the lower accuracy in this, we try to do hyperparameter tuning to improve the performance by adjusting the learning rate from 0.001 to 0.01, but the improvement, there was no improvement at all. So we conclude that hyperparameter tuning alone cannot improve the performance in complex datasets like CIFA-10. Rather, we require more deeper architecture, more experimentation and analysis, and then maybe a combination of different techniques can help improve the performance on this CIFA-10. Thank you.